Hey, how's it going, 11:30 lab? So once again, I am sorry that I was not able to meet with you on Teams on Tuesday. Unfortunately, I wasn't feeling really good the night before, and my boss recommended that I did not come here. But I feel awesome, I feel great, and I'm ready to do this lab with you guys. So, from my understanding, you guys are now working through your kinematic equations of motion, and essentially have been learning how to deal with straight line motion with actual constant acceleration. And so this lab is supposed to basically give you guys a proof that sure enough, with straight line motion, we do in fact see a constant acceleration just like we did when we did the free fall lab. But this time we're going to be seeing basically a cart, this little guy right here, actually going down the ramp. And so what we should observe is that regardless of the fact that we may measure our velocities from 10 centimeters out to 20 centimeters, out to 30 centimeters, 40 and 50 centimeters, that the acceleration, regardless of the initial velocity and the differing final velocities at those distances, should all be calculated to be the same. So how do we do that? And this little guy right here, well, it's kind of fun because it does have a plunger, and well, we used to actually have fun with these things down the hallway. I'm surprised I didn't get in trouble doing this when I first started working here. So what we're going to be doing today is allowing for our friend the GLX to actually take measurements for the initial velocity when we allow the cart to move from the start. And we take the initial velocity here, and then it will actually measure the final velocity in this gate. And so by having our initial velocity and our final velocity, we're going to be able to calculate that acceleration that occurred in between those gates. So how do we do that? How do we deal with the kinematic equations of motion? Most of the time when I've taught the 1030 class, and every time I've taught the 1130 lab, students always ask me the exact same thing. Well, Mr. Morley, we got four equations. How do we deal with the four equations? Oh, oof. Right, four equations. Which one do we use? And much of the time I see students basically just trying to grab for the first equation that they can get. And oftentimes they get confused because I'll hear somebody say, well, there's multiple variables. How do I solve the equation with multiple variables? Well, if we have an equation with multiple variables, we may need to think about our assumptions, not only the assumptions, but also the data that we're going to be taking, the data that may be available to us. In this case, we're going to have our displacement and also our velocities. And so if we consider what data is going to be available, well, first thing you should always do with the kinematic equations of motion is just sit back and look through each of these equations and say, well, what do I have that's actually available for me? And in this lab, the entire intent is to prove out, once again, that acceleration is going to be constant regardless of the displacement that we're going to change here, and regardless of the fact that we're going to have varying final velocities. So we want to be able to calculate that acceleration. So if we look at our kinematic equations of motion, well, let's see here. Let's see what we got. Well, we will have our final velocity, we will have our initial velocity, and well, that's the one that we want. Acceleration. We want that acceleration. Got a problem though. Don't have time. Is there any way we could get time from the next equation? No, because that has acceleration, and that's actually what we need. Well, how could maybe the third equation work? Could this actually be the one that we need to actually utilize? And sure enough, it actually is, because for 5 different settings of differing displacements, we're going to have our final velocity, we're going to have our initial velocity, and we're going to have our final position and our initial position. And so due to that, then we are actually going to be able to calculate our acceleration just fine. So from there, guys, we'll be able to take that acceleration and later on be able to determine the actual time it took for that cart to move in that straight line motion. So, as far as the lab procedure that normally you guys would be doing in here, well, the setup's already done. And so generally for each of these distances, we have a distance spaced here, basically 10 centimeters, and I'm going to do 5 runs of allowing for the cart to move right through basically these 2 photo gates. And it's going to take the initial velocity and then the final velocity. I'm going to do 5 runs of that and then get basically an average initial and final velocity. And then from there, I'm going to move down this photo gate to 20 centimeters separated, and then allow for basically that cart to go again 5 more times, which I'm going to take the average initial velocity, average final velocity, and basically repeat that for 30 centimeters and 40 centimeters and 50 centimeters separated from the initial photo gate right here. And once we take that data, then it's going to be up for you guys to go in and utilize our kinematic equations of motion in order to actually determine that acceleration. And once we determine that acceleration, we're going to be able to determine how much time it took for that cart to travel between those 2 photo gates. So, everybody ready to get started? Let's knock this out. So for the first one here, I'm going to allow for the cart to go 5 different times, and during each time I'm going to write down basically the data that I gained from the GLX, and at the end I will show you that data and we will call it good. Start moving forward. Let me get a pen first though. Alright, I love this lab. And guys, the thing is about the kinematic equations of motion is that once we start utilizing projectile motion, we're going to see how the equations are actually going to vary due to the assumptions of the system. Remember that the assumptions of this system is that we're working with constant acceleration. Okay? So, let's see if we can calculate that constant acceleration. Remember that the constant acceleration that we have for this cart traveling is due to the fact that gravity is pulling it down. But we're not going to see 9.8 meters per second squared, because now we have a horizontal travel and not just a free fall. Alright, let's knock this out. So, I'll start with the first run. And here we go. Alright, first run, that was 1.12 meters per second. That was our initial velocity. And the velocity in gate 2 was 1.36 meters per second. So I'm going to do this 4 more times, and then I'm going to write down the average initial velocity and the final average velocity. Okay, so this is our second run. Alright, so 1.07 and 1.34. Let's try it again. Okay, 1.12 again. And 1.35. Ooh, I may have been off a little bit from that second run because I may not have put it all the way up at the very, very top of this bumper. Let's see if we can get 1.12 again. 1.12 meters per second and 1.37. Let's do our 5th run here. Alright, 1.12 again and 1.36. A little bit of variance because I kind of screwed up just a little bit. But that's okay. The average initial velocity that we had for this one was 1.11 meters per second. The average final velocity was 1.36 meters per second. Okay, so I'm going to stop the GLX and I'm going to maneuver this down to 20 centimeters separated. So we should have the same initial velocity, but now a greater velocity in this gate. But I bet you that acceleration is going to be the same, guys. All right, let's give it another try. So another group of 5 runs in which we're actually going to get the average initial velocity and average final velocity. Let's check it out. All right, run one. Here we go. Rock and roll. Ooh, 1.14 with a final velocity of 1.59. That velocity, sure enough, increased. 1.13 and 1.59. Let's try it again. Third run. No dice. 1.14 and 1.58. Fourth run. Nice. 1.14, 1.59. And fifth run. 1.14 and 1.58. Awesome. So the averages of both the initial velocity and the final velocity for this run. Initial velocity, the average was 1.14, so a little bit different. And then 1.59 meters per second for our final velocities. So just as we expect, with constant acceleration, that final velocity should have changed, and sure enough it did. So we're going to maneuver this down. Now we're going to have 30 centimeters separated from each other. 30 centimeters. So let's give this a try again. I'm going to start the GLX. All right, we're rolling. First run. 1.12, 1.76, our velocity increased. Second run. All right, 1.13, 1.77. 1.13, 1.76. 1.13, 1.77. Fifth run. All right, 1.14, 1.77. So our averages right there for our initial velocity was 1.13 meters per second. And then our average final velocity was 1.77 meters per second. Okay, let's move this down. So we're going to do 40 centimeters separated. Is this kind of weird because I feel like I'm calling out these numbers and I should be like at an auction. I wish I had that talent to speak really, really fast like that, and I think that would actually make this lab very, very interesting if I was running out these numbers as if I was an auctioneer. But maybe in another life. All right, here we go. 40 centimeters separated. Here we go. Come on now. Now we're running. First run. Awesome. 1.1 with a final velocity of 1.9. Let's try it again. 1.14 and 1.93. Let's try it again. Could have been there. It could have been some possible error in the way I let things go or set it up. Could be. Don't know. 1.11, 1.92. Need to be more consistent here, Morley. Come on. All right. 1.14, 1.94. And fifth run. 1.14, 1.94. Our average initial velocity for that run, 1.12. And finally, we got 1.93 meters per second for that final average velocity. So we need to do 50 centimeters separated from each other. All right, here we go. 50 centimeters. All right. Final set of 5 here, guys. All right, here we go. 1.14, 2.08. Ow. 1.13, 2.08. Third run. 1.1, 2.06. 1.1, 2.07. and 5th run for our data taken for today on a Thursday, rainy Thursday. It should have been on Tuesday, but we know what happened. And I just did what Miss Smith told me not to do and just let it hit the thing, and well, luckily it didn't roll off the table and, you know, break it, because then I would be in trouble. All right, so let's see here what we got for the average initial velocity. Once again, 1.12, and then 2.07 meters per second. So that's the data that we're taking for today, guys. So we're going to take basically those averages, that average initial velocity and that average final velocity, and you guys are going to go in and apply it to this equation here. And then from there, calculate that acceleration. For each run, we know our point of origin here is just going to be 0, and then XF for each run is going to change between 10 centimeters to 20 centimeters to 30 centimeters to 40 centimeters and then 50 centimeters. Later on in your analysis, then you're going to go and calculate basically your time, and you can actually either do that with either of these equations, because now you'll have your acceleration in the first equation here, so your other two variables, VF and V naught, you'll have. For here, if you use this equation, you have XF, X naught. Then you actually also have V naught and your acceleration. So you have a quadratic equation to solve, but you know, if you want to do it that way, that's totally fine. So just remember, guys, when you're trying to decide which equation you want to utilize, find the equation that includes all of your current knowns, except for maybe one. And then maybe, just like we're doing in here, we're taking the acceleration and then using that to find another variable and determine how much time that it actually takes for that car to move from X0 to XF. Okay? And at the very, very end of the lab, what you're going to do is actually set up basically charts in Excel, and you're going to plot position versus time, velocity versus time, and acceleration versus time, and then you're going to put a trend line to that. So make sure that when you guys upload your data to me, your calculations, that you're also uploading basically that Excel file so I can take a look at that as well. So let me show you guys exactly what I have as far as the data, so that you guys can see what I've written down for you today. All right, we'll maneuver the camera down so you guys can see. And sure enough, there's the data that we took for today. So sure enough, most of those initial velocities were just fine. And then the final average velocities definitely changed. So anyway, guys, that's all I got for you today. So just make sure you go through by next Tuesday. You know, this was my mess up because I didn't feel good. So, you know, by next Tuesday, make sure you have that uploaded. And if there's anything I can answer as far as questions for you guys, go ahead, don't even hesitate. Shoot me a message in Microsoft Teams, and I will get with you guys and answer your questions. Okay, fantastic. Hope you guys have a great rest of the week and an awesome weekend. And I'll see y'all on Microsoft Teams on Tuesday. Take care.